Test. Can everybody hear me now? Test, test. Okay. It looks like everybody can hear me. Let me share the screen. Make sure that everybody can see the screen. Okay. Dr. Ashur, can you see my screen? The cover sheet of the presentation? Okay. Okay, good. Thank you so much, Dr. Ashur. I really appreciate it. Good afternoon. I'm here in California. It's 11 o'clock a.m. and I understand. Paul Besmertnik. It says louder. Okay. Tell me if everything is okay. I'm going to test it. I'll make sure the volume is higher. Okay. I increased the volume. Is everything okay now? Okay. If there's a problem, let me know in the chat box. Okay. Okay, good. Thank you, Mr. Besmetnik. Thank you. Okay. I'm not sure, Dr. Ashur, how many participants we have today. If you could let me know, that would be great. But again, it's a privilege and honor to be here today, presenting this webinar to my colleagues and other participants. Generally, in the past, we've had seminars and webinars through different institutions, including NEH, that is presented throughout North America, and we have participants from Canada, US, South America, and so forth. Okay, let's jump into this presentation, causes of structural failures and forensic engineering process. Okay. Yeah, looks like I'm trying to get the next pages. There's a glitch. Bear with me a few moments. I should be able to see what's going on. Let me stop sharing for a few seconds. Okay, share again. Oh, now let's start moving forward. Okay. So, Okay. So here's a brief introduction about myself, my credentials, my background. I have served as an arbitrator, structural and civil engineer, educator, and expert forensic consultant for over 40 years. I've been providing expert services for over approximately about 200 litigation matters throughout North America, as Canada and US. And I have I'm licensed in 12 states and as well as Canada, and my work, design work, investigation work, has been throughout all these 12 states and Canada as well. I had the privilege being interviewed by History Channel on a documentary that has had over 10 million views so far, and other media and news agencies. And okay, good. And I've been providing presentations, structural engineering and structural engineering subjects since 2007, probably about 50 of them so far. Okay. So this webinar today is going to be discussing the causes, and then we'll go over those in depth. And also, I will provide you with some case matters that have been involved and retained as an expert, so we can have some direct experience about these issues. So generally, there are 12 sections on this: structural engineering design errors, which can be one of the causes, defective construction, material deficiencies, excessive loading, deterioration and degradation, these are the course outlines. Documenting the failure, preservation of the evidence as relates to the chain of custody, conducting investigation and research, field protocols and tests, determining the causation and responsibilities, learning from the structural failures, example of historic failures. Okay, so let's begin from structural engineering design failures. So here for now we have 5 topics, and I go over each topic and I provide you some examples, real world examples. Failure to address subtle structural issues, failure to understand the project's objective, understanding the demand requirements, insufficient design verification, failure to validate design assumptions. Okay, so let's take a look. Number 1, subtle structural issues. I think right now in my mind, I have 2 cases that I can discuss with you. One case is, this is a case that is over, and you can Google it online and look at the details if you want. It's about car manufacturing, a world level car manufacturer. I prefer not to mention the name, in Alabama, one of their facilities in Alabama. They hired a professional engineer to design these robotic arms on their production line, and the structural engineer was going to be designing the moment frame, three-dimensional moment frame, like 40 feet, 40 feet, 40 feet each dimension. And the robotic arms were going to be installed on various sections of this moment frame, more particularly on the beams above. And these robotic arms were going to move back and forth. What happened is the engineering firm did the design. The contractor built it. Robotics arms were installed. But then after a few minutes of the work, because of the magnitude of the error that was experienced by the robots, the entire production line shut down. The way their system worked is that if the robotic arm experienced excessive vibration or excessive displacement during the operation, then automatically a system would shut down everything. And so anyways, this was a multi-million-dollar damage, and I was retained as an expert on this, and we found out that the robot manufacturer required about 2 millimeter tolerance of the displacement during the work of the robot. And you might think that, okay, what does this 2 millimeter have to do with this moment frame? I'm going to explain that in a few moments. When a robotic arm moves back and forth on a beam of the moment frame, it's a different story than when it's sitting still. When it's just sitting there, it's only like about 500-600 pounds or 1,000 pounds of force gravity loading only. But when it moves horizontally, it's a completely different story. As soon as you start moving the robot, and as soon as you stop, you create an additional load, horizontal load, in addition to the gravity load to the system. And that system has to resist that force, whatever it is, and it exhibits a displacement, lateral displacement. That displacement was the problem. We found out that the structural designer never took that into account. They did a 3D analysis of model and everything, but they never took into account that how sensitive this tolerance is. 2 millimeter is extremely limited, and for a 40-foot tall moment frame, approximately 40 feet tall moment frame, that would be extremely difficult to achieve, but it is achievable. You just have to make the frame members rigid and the connections and so forth. But what we had there was magnitude of several inches, which didn't help. So anyways, this is one example of addressing a subtle structural issue. Like the moment frame was perfect, seismically was fine, gravity was fine, but for this particular application of robot performance was failure. It was a failure. It couldn't perform as required. So eventually, the solution was to stiffen up all the members, and then it worked. Started working. Okay, that's one example. Another example, let me give you, is a little bit. That was in Alabama. The other example happened here in California, and I've seen several cases similar to what I'm going to explain to you now. The case involves a staircase. A large staircase, let's say about 20 feet long, one flight, 12 feet or 14 feet elevation gain, and about 30 feet length. And on one single stringer, steel tube single stringer, on the center of the threads. So the threads started going up like about 8 feet or so, and then there was a landing, and then again another 6-7 feet or so, total maybe 14 feet. This is in a high rise. In a high rise building, the top 2 story belonging to world-class company, which again I prefer not to mention. If there are 3 top technology companies, that's the level we are talking about. And they wanted to connect these 2 top story in this high-rise concrete building, and they cut a hole. They put this staircase with a single stringer, as I said, in the center, and the designer did the design. It got manufactured, and then the day the users, the employees of this company, tried to use it going back and forth, it was a nightmare because the vibration, it was so large, and so the magnitude of vibration was so high that people on the upper level in the office, in the adjacent area to the stair, they could see everything, monitor everything shaking, and this was not acceptable. Now, this is another example that, okay, the staircase is perfectly fine in terms of meeting the life safety requirement. It's not going to collapse under gravity loading, but we discovered that the vibration criteria was never taken into account by the designer. We went through all of the designer's computations and found out that it was essentially just a simple beam design, stringer design. The frequency, the stiffness of the stringer, and the threads were never taken into account. And let me add one thing here. In addition to that sense of being uncomfortable and causing these vibration throughout the offices adjacent to the stairs, there was another problem. The other problem was that these threads, they were cantilevered on both sides, right? Just on the center, there was a stringer, but then they were cantilevered on each side. So 6 feet long, 3 feet cantilever on each side. And the problem with that was that the threads were excessively exhibiting displacement. And one thing that you need to be aware is that if you have your thread covered with wood or carpet, or wood covering or carpet or similar material, you don't have to worry about the deflections. But as soon as you have very fragile material, which are usually expensive, such as terrazzo or similar material, then you have to go L over 720 in order to make sure that you don't get any cracking. Okay, so L over 240, L over 360, L over 480 is what we generally use for standard construction material. You know, not extremely fragile like porcelain, like terrazzo. As soon as we go into these areas, then the deflection areas on deflection criteria almost doubles. And there are certain publications by certain institutions in US that provide these guidelines that, hey, you need to do that. So that was another issue. So that failure number 2 item here, failure to understand the project objective, that's the example that I provide you. Unfortunately, we found out that the designer was not even aware of this issue and did not have this implemented into his computation. Okay. Next item, undermining the demand requirement. So whenever we structural engineers provide services, there's demand. 90% of our work Like I have investigated and designed probably several thousands of structures throughout my career. 90% of these design projects that we do or investigations probably are simple, straightforward. There's just a certain steps that we take, and it's just routine and okay. But I think about 5% of them can be very, very, very tricky. Not necessarily complex, they can be tricky. And we have to watch for that. When I say tricky, I mean they're like a trap. If you are not extremely careful about those 5%. Projects. So let me think about some of the examples that I can tell about the demand requirement. Underestimating the demand requirement. Okay, I'll give you another example of my own work again. About few years ago, there was a roof collapse in Southern California, a big warehouse, 70,000 square feet warehouse that was a facility that they froze strawberry and they send it with jet to Japan every single day. And what happened is a solar installation company came and approached the owner and said, hey, I can put solar panel on your roof and you can save millions of dollars over the course of several years. And they did. They came in on the roof and they installed the solar panels and with the balusters, with the weights, because the solar panels, they can uplift because due to wind forces. So they put the balusters and that's it. Everything worked for about 30 days, but after about 30 days, 5 o'clock in the morning, the supervisor of the facility was entering the facility and he heard creaking noise, heavy noises, sound of breaking, these 72 feet long, 6 feet tall glue lamp beams. They're coming down. So anyways, he did something and he prevented the total collapse, but part of that roof collapsed and probably like about 20% of the roof collapsed and the beam came down actually. And thank God nobody was hurt or injured, but underestimating the demand requirement. One tricky thing about wood design, which is completely unique when you compare it with steel design or reinforced concrete design or post tension or any other material, is that in wood design, when you look into National Design Specification, you have a specific factor for type of load. If you have live or you have dead load or you have roof load, it makes a difference in your allowable stresses. In a steel, that's not the case. In concrete, not the case. Masonry, no. Post tension or aluminum or glass, no. But in wood, you do have that low duration factor. So why do I say this about this roof load is that the designer assumed that, okay, I have 10 or 12 pound per square foot of live load for my roof live load. And if my load, if my balusters load, the weight of the resisting the uplift, if they're less than 12 pounds per square foot, I'm good. That was the understanding. Okay, but you have to understand we have a low duration factor of here, when we have a combination of live and dead, we can increase it by about 15%. But as soon as you remove the live and you only put dead, in all our calculations, we have to reduce the, not only we cannot give 15% additional stress to our allowable stress level, we have to reduce it another 10%. So we only can use 90% of the allowable stress loads, allowable stresses on wood when we are only working with dead load. So from 115% become to 90%. So that's a 25% decrease. And so, yes, you had 12 pounds per square foot dead and alive. The Golan beam calculates fine, they can handle everything. But as soon as you say, okay, now instead of that 10 pound of live, I'm going to put 10 pound of dead. Okay, then you can't calculate it based on 115%. You have to calculate based on 90%. And wood, usually, based on my experience for the years, usually they don't fail immediately. It takes a long time, like a few weeks or so until they collapse. So that's another example of the demand requirement. Insufficient design verification and failure to validate the design assumption. Design verification, whether it's wind, whether it's seismic, whether it's flooding, whether it's fire, whatever design criteria that we have. Again, sometimes they can be tricky. And all these design errors don't happen necessarily on simple routine projects. The routine project that we do on a daily basis. Sometimes there are projects that are a little bit different, and that difference we have to be very careful. And we don't get paid for those tricky projects. We don't get paid extra for those tricky projects. We don't. So, but we just have to pay a lot of attention to them. And sometimes these tricky projects, if we don't notice it at the time when we're providing the estimate or proposal, then we have to absorb all the cost and bite the bullet. For example, that staircase that I mentioned to you, that staircase, in reality, our estimate was that it was going to require about 40 hours of work, but apparently the designer put something like about 10 hours. Just my understanding is that he didn't just comprehend the extensive work that it required, and sometimes, you know, that can be a problem if we don't understand the trickiness and the complexity of some of these projects, things that are minute, very subtle, they just slip. And we are very lucky if we find that in the middle, because the worst case scenario, we just lose $10,000, $20,000, but at least we don't create a problem with our projects. So, and the next item, failure to validate. Okay, we have, let me see, I have to make sure that my pace is okay. So this is a slide 6, and right now is 11:30. So, all right, defective construction. That is generally not necessarily relates to engineers. You know, we have about 20 participants today, and generally the audience are from structural engineering field, from sometimes mechanical engineering field, from architecture, government agencies such as inspectors and so forth, and contractors. So here, when we talk about this defective construction, it doesn't necessarily, obviously, is not any oversight. It's not caused by oversight of an engineer, the structural designer. It's not related to us directly, but the problem is that when they occur, the designer gets involved also into the dispute. Then obviously it takes time to prove that, okay, there was no fault from the structural engineer, and it was just simply something to do with the general contractor or his subcontractors. Okay, so let me introduce to you two term of arts. Two term of arts: latent versus patent defect. Okay, I went to law school about 2.5 years so back in the day before I became forensic structural engineer, and at that time I became familiar with some concepts in law. This is one of them. So latent defect is different than patent. A patent defect is a defect that a lay person can discern. For example, you walk into a structure, you see cracks, you see displacement, you see distress. They're very obvious. You don't need to be an engineer. You can be a painter, or you can be a chef, or you can be a surgeon, and you can see these. You don't need to be trained in our field. But latent defects are different. It requires a skilled and qualified structural engineer to detect them. And most of the time, even a qualified general contractor cannot discern them or objectively establish their existence. So, for example, there is a problem with the structure, and they notice some problems, but they don't know what it is. They cannot define it. And you walk in and you use your instrumentations, whatever instrumentation that it could be. It could be a Schmidt hammer, non-destructive instrumentation. You bring your Schmidt hammer, you bring your GPR, ground penetration radar instrumentation, you bring your manometer instrument or other instrumentations, and you go through the buildings and you find out why values that you get from your instrumentation that, okay, and you bring into the office, you analyze all the data, you incorporate, put into your in writing and in a report, and you present it to your client, say, hey, these are the latent defects that you were never aware of it. You had some other problems that triggered this investigation. And that's the definition of latent defect that we generally deal with. Sometimes an owner or occupant of the structure never find out there was latent defect until they sell it. When they sell it, the next owner finds out about them, and then that's how. Okay. How do we end up having defective construction? There are several ways. Undocumented foreign material. I've seen many examples of this. Erection and fabrication issues. I've seen many examples of this, and I can share some of them with you as long as the time allows. Construction sequence, poor workmanship, defective temporary support. Item number 5, defective temporary support, and item number 2 can be related sometimes, because when you erect a structure, you need to provide temporary supporting at the same time too. So these two can be related to each other. I give you an example of number 2. Several years ago, there was a hospital here in California, Southern California. I'm located in Southern California. So there was a hospital, 5-story building structure, steel frame. And one thing about California, which is, I believe it's unique, you don't see this in anywhere else in the world, maybe in Japan, I don't know, but in California, if you have a building structure that is a hospital or urgent care or acute center, you don't need any construction, any permit. You don't need any building permit from the jurisdiction authority or city. But you do need a permit from HCI. HCI is an entity, an agency by the government that have top-notch structural engineers, mechanical architects, and so forth. They do the plan check review probably 10 times more stringent than the Department of Building Safety. And the process usually takes at least a year or two to go through to a plan check review with them. So anyways, the name before was OSHPAD, Office of Housing and Administration in California. Now is changed to HCAI, HCAI. This organization was in charge of that hospital that I just mentioned, 5-story. And what went wrong with that building, which ended up in a multi-million-dollar dispute, was that the fabricator, a steel fabricator, they sent all the material to the site, and the erector erected all of them, all 5-story. And when the OSHPAD inspectors came in and they had to inspect it, and they found out that with these welding for the moment connections, they were defective. And guess what? The only solution was to disconnect everything, bring them down to the ground, and start all over again. That was the only solution. And so that's an erection and fabrication issue. There was some kind of miscommunication that unfortunately caused that problem. Defective temporary supports, I've dealt with many cases that was caused because of defective temporary support, and some of them causing some serious injuries for the workers. I go through them. Again, I have to pace myself. We have another 60 some slides. So material deficiencies. Most of the most common construction materials are concrete, steel, wood, CMU, aluminum, and glass. These are the most common. Concrete, you have pre-stress, you have post-tension, different types. But generally speaking, they fall under these 6 categories. For concrete, the deficiencies can arise from concrete mix design. Again, these are the cases that I've seen myself been involved. Improper reinforcing placement, improper curing, inadequate vibration, and on-site water and additive addition. I'm sure as you participants, as whether you're a structural engineer or architect or contractor or inspector or other professions in our industry, in the construction industry, you're familiar with these issues. Concrete mix design, they're not always 100% accurate from the batch that they mix this and they prepare them. Sometimes there are flaws, sometimes not a lot, probably maybe less than 0.5% of the cases that can result in problems. Sometimes serious problems because the concrete is really soft. I've seen cases that the concrete testing result was like 1,500 psi instead of being 2,500 or 3,000 psi. Improper reinforcing. again, we're talking about material deficiencies here. When the reinforcing either does not meet the strengths that is required by the building code, or whatever. Let's say, let me give you an example. Let's say you are designing a bridge over near the ocean here. We have a lot of bridges here by Caltrans. They're a government entity that does is responsible for the highways and bridges. Either a bridge near the ocean or a structure near the ocean. Either way, your concrete reinforcing is going to be subject to chlorine from the ocean. And this is a real issue, and I see it every day with my own eyes here. If you use standard rebar, when your concrete is exposed and near ocean is exposed to chlorine from the ocean, your concrete is going to fail very soon. When I say very soon, I mean within 3 to 4 years. You can have a spalling, you can have all kind of problem, and you have to remove and replace the whole structure. I'm sure some of you are familiar with the epoxy coated rebar. Those are the green color rebars. You can use them, but even those ones are not really resistant. And what these days are used is stainless steel rebar. Stainless steel rebar, they're very expensive, but that's what the government here, the Caltrans is, for example, is using for their bridges, because you're talking about like a $2 billion bridge and a lot of financial impact if the bridge has to be shut down for replacement. So nobody's going to take any chances just for maybe about $1 million extra for the type of the rebar. Now, improper placement, that's the next item of the rebar. That improper placement, it is something that can cause by the subcontractor or contractor, but I have categorized it here because it's related to the material. I've seen cases where the rebar in the concrete beam or concrete slab, this mostly happens in concrete slab because the space is limited. Then, for example, the negative rebar is not placed where it's supposed to be. Like, for example, instead of 1.5 inch coverage from the top, it has like 2.5 inches of coverage. And you know that changes the lever arm between the bottom compression face to the top tension, the centroid of the rebar. Because when you have negative bending, it's usually normally is on the support, and on the support you have bottom in compression and top on the in tension. So if you have a concrete cover on the top instead of 1.5 inch or 1 inch that was specified in the plans, you get 2.5 inches, and your slab is only like 7 inches. That results in a big problem. It can impact everything. It can impact deflection. And yes, deflection is not only caused by insufficient moment of inertia or insufficient rigidity, modular elasticity, but it can also cause by insufficient reinforcing strengths. It can cause that. Okay, improper curing. That I don't think I need to explain that. When the curing is not done properly, either because of the excessive heat, the watering was not performed properly, or extremely cold weather condition, which again, the concrete wasn't protected during the first several hours of curing and so forth. inadequate vibration, again, you know about that. And that occurs, generally speaking, when the vibration for some reason is not performed. Usually, this happens in deep um, uh, deep sections, such as walls, shear walls, or retaining walls, or deep beams, or sometimes columns. That happen usually in the slabs, or slabs doesn't happen very often, but it does happen on deeper sections, as I said, and sometimes even in beams. I've seen in like 2 feet beams. When you walk into these garages, underground parkings, you look up and you can see some of these honeycombs that are evidence of inadequate vibration, which which in some cases they can't cause any problem, but there are cases that they can cause issues. Anyways, item number 6, on-site water and additive addition. I'm sure you're all familiar with that, and I've seen many cases like that myself. That water cement ratio is very crucial. If they go more than, if the subcontractor wants to do the job quick and go leave the site, go to another site, they might add excessive water or additive and do the job quickly. And that I've seen also. Okay. Now the next material, steel. Error in fabrication and erection that I explained to you earlier about that hospital. Improper installation of the connection. I go through and then I explain. Inadequate weld quality. That weld quality that I explained for the hospital in California, that is another example, especially when you have thick layers of welding. It becomes critical. Misalignment of the members, localized failures, and lack of environmental protection. Installation of the connection, the second item, that even the small connections of, let's say, small I-beams to the girders, that sometimes can cause issues if they're not done, installed properly. Quality of the work, I mentioned that, and most of us are familiar with that. The number of the passes that the qualified and licensed welder here in Southern California, in a lot of jurisdictions, welders have to have certification from the jurisdictions. For example, City of LA does not allow anybody who has not obtained a qualification from the city to perform welding for major buildings, main buildings, or most of buildings. Misalignment of the members, when there are two, for example, horizontal beam members are connecting, the misalignment instead of being aligned. Localized failure, anything from lateral torsional buckling to other localized issues, and lack of environmental protection. Environmental protection, you're talking about, again, chlorine and corrosion issues and so forth. Believe it or not, I went to a big, very big facility here in Southern California, and I was inspecting and providing assessment for the building. And one of the columns, it wasn't a huge column, it was like a W12 column. It was exposed and it was outside. And on the base, it was so corroded that there was actually a hole in the middle of the web. And I put my finger there and took a picture, so it gives a sense of how big and how bad is this. Yeah, so that again, that facility was near the ocean, probably within let's say 100 yards away from the ocean. Okay, now next we go to wood. Wood, very, very common in Europe and in US and North America. Not very common in some other countries because of the limited resources of the wood. But wood, being such a popular material, it has its own unique issues. Moisture content. We know that, the moisture content needs to be kept below a certain level. We look at NDS, we can see that if you have a high level, more than 19% of moisture, you have to reduce your allowable stress. But it's a little bit tricky here. Let me explain to you. If the moisture content within the wood material is kept low, like below 16%, 10% or so, you don't get any problem with dry rot, insect, and fungus, item E. You don't get that problem. If it's high, close to like 50, then you get these problems. But something very surprising, if you go really, really high, then your wood will be sustained for hundreds of years, no problem. I give you an example. Venice in Italy is built on wood piles, and all these wood piles are submerged in water for hundreds of years, and they're there and they perform well, and there's no problem. So that's a tricky issue with wood. Now, expansion and contraction of wood material, that's something that you can deal with that in exterior cases or on roof application when the insulation is not proper. You can have expansion and contraction. And then I've seen that clients complain about noises at night or bad, very loud noises, not just simple creaking, and that they scare them. Then third item, lack of environmental protection. Again, a wood, if it's exposed, it needs to be protected by a stucco, waterproofing material, and so forth. And if it's not, then it will deteriorate. And one thing we have to be extremely careful here is about manufactured products. Okay, so we have two types of material in wood. One is sawn lumber, traditional wood material that have been used for thousands of years, and one is manufactured products, manufactured or engineered wood products. These has come into the market since like glulam have been around for a long time, but when I'm talking about like I-joists, for example, or microlams or Paralam or laminate, these kind of material that are different than glulam beams. But regardless, glulam beam has not been around for like thousands of years. They're recently relatively new, a few decades, several decades. Paralam, glulam, microlam, and I-joist since the 70s. Now, these are completely different material. Their behavior and their performance when they're exposed to water. When you have sawn lumber joists exposed to water once for a few hours or a couple of days, usually once they get dried, they can continue their performance and service for many, many, many years. As long as it's limited, it's not like years submerged in exposed to excessive moisture. As long as it's just limited to a few hours or a couple of days. But that's not the case for engineered material or glue and beam or I-joist or parallel. That's not the case. Also OSB, also plywood. OSB, plywood, these I-joists, glue and beams, these have one thing in common, and that is glue. And the glue that is used in these materials is very susceptible to water intrusion. Once you have water intrusion in these, you can look at the manufacturer literature. They state that very explicitly. Once these materials are exposed to water, they lose their structural integrity. So you have to be very, 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 very careful. I remember in the beginning of my practice about 40 years ago, 35 years ago, one contractor used a parallel beam for exposed application. And after a rain, he called me and said, "Hey, Casey, my beam is deflected 5 inches, a parallel beam." And for some reason, he didn't have protection at that time. I don't know, was during the construction or whatever it was, that beam had to be thrown away. You can't use it anymore. And unlike sawn lumber. Anyways, so that we need to pay attention. Lack of proper maintenance, dry rot, insect, fungus, and construction error. Construction error, I think, is self-explanatory. Okay, now I'm going to provide you with one of the cases. Bear with me a few seconds. Let me check something quick. Okay, let me go back. Okay, I'll go through these quickly because if I don't, then I won't be able to cover everything. Okay, it's 12 o'clock, so we have 1 hour left. And right now my slide is number 14. So I have another 60 slide left. So this, I'll go very quickly. This is one of my own cases in Washington State years ago. And this is after the fact, after they rebuilt, let me see. No, this is old. Yeah. This is the old case. And that failed, and then they rebuilt it later. But this is the old case. So these handrails, and you can see, the owner invited his guests from other states. They came here. They, in the evening, they wanted to take a picture. They leaned against this here, this handrail, just like this diagram that we computed in the illustration, and he fell. And they fell. Both of them fell. And this is the fail. This is the connection. As you can see, the connection was just with 2 screws. And obviously, this doesn't meet the building code requirement and all those forces that is required for the handrail. And there was no engineering involved. There was a flipper that did this. So it failed. And now this is the new one. This is the new one. You see the 6x6 posts here bolted to the system versus those 2 tiny nails that caused the failure. Okay, this was a case that it resulted in severe injury. Another case, one of the cases that I was expert involves a roof sheeting. Here is OSB material. OSB material. This case, the owner bought the land. Hired a contractor built this brand new home. After a few months, the owner noticed that the roof was wavy. It was not flat. So we went in and we found out that there was no gap between the OSB. Again, that contraction and expansion that I was speaking a few maybe minutes ago, that's what it caused the problem here. There's no spacing here. And when you go into the APA publication, American Plywood Association, they do require this 1/8 gap. And the general contractor was not aware of that for some reason and cause problem, dispute. Material deficiencies, masonry, CMU. When we're talking about interior application, let's say you have a CMU wall, whether it's above the level or under ground application. If you don't have adequate waterproofing, if you don't have adequate drainage, the rebar will rust in a matter of maybe few years. It will rust, and they make the wall out of commission. Sometimes the masonry units, the shells are deficient. Sometimes the mortar, just like the concrete design, is improper. We have thermal expansions that, we have to have those construction joints every 30, 40 feet or so, depending on the region and configuration of the wall. And and the deficient expansion and control joints that I just explained. Okay. Excessive loading. Concrete, steel, wood, CMU structure respond differently to excessive loading. Sometimes the deformation is elastic, they can come back. Sometimes it goes beyond elastic, it goes to inelastic, and sometimes go to plastic, that depending on the material. Material design versus load duration. That load duration that I explained earlier is only applies to wood, nothing else. And lack of warning of brittle material. We are all familiar with that. Concrete material don't give any warning, God forbid, when they want to collapse or fail. The steel does a little bit, wood does, but not concrete. This is an example of, this is in Southern California, and right at the ocean, there's a handrail. This handrail on the left-hand side was completely vertical, was not exposed to waves. But this front handrail was exposed to waves, forces, and also the chlorine from the water, the chloride from the water. And as you can see, it bent and it displaced like about 4 feet. And actually, after 2 years that I went to this location, completely this handrail was gone. It was washed away. There's nothing there now if you go. Anyways, another case. So this, I just wanted to let you know the impact load of the waves. They can cause this much deformation in the steel. Or, once they come hundreds of times every day over the course of years, they can cause this kind of deformation on a steel. This is a solar panel application here in Southern California in a residential home. Everything on this side looks okay, is on the roof, but on this side, something odd. You can see it's elevated, okay? It's not sitting on the roof, roofing. You see it's elevated, you see these supports, and that was the cause of the problem, because the wind can become really, their forces can become really high when you're dealing with this kind of condition and configuration versus when they're sitting directly on the roof. And as a result, when we went downstairs and look at the ridge beam and some other material, they all had these kind of failures and problems. These are the temporary shoring that we required. We didn't believe that the condition was safe, so we required temporary shoring. So deterioration and degradation on item number 5. Concrete, which deals, you deal with corrosion and spalling a lot of time. Steel, we deal with corrosion and incompatible material and fatigue and cyclic loading. Then we go to next. Wood, weathering, dry rot, we discussed that. CMU, weathering, water absorption, freeze thaw, damage, corrosion, mortar degradation. Okay, let's go back to 5 in the beginning. Some of them I need to explain. The other ones you know, you're aware. Concrete, we talk about this corrosion and the spalling, as you might know. Rust takes several times more space than steel. So when you have a corroded steel inside concrete, it expands and nothing can stop that expansion. And ultimately the concrete breaks and fall, and that's called a spalling. Corrosion, we talk about that. Incompatible metals, when you have some cases in bridge design and also in structures, when you have a steel with another metal like aluminum being in touch, it can cause deterioration, degradation of both materials because they're two incompatible metals. You have to have either insulation between them or you have to have the same material. And these can cause serious consequences. It's not a joke. It's just because of the different chemical. Fatigue and cyclic loading is extremely important. The cover sheet of this presentation is actually a case that involves cyclic loading and fatigue. And cyclic loading, when you have hundreds of thousands or even anything more than 25,000 cycles can cause failure if it's not designed properly. There's a specific section in AIAC, American Institute for Steel Construction, that addresses cyclic loading and fatigue. And whenever we are doing a design, we cannot use simple steel design. We have to go through this cyclic loading and fatigue analysis, and it's extremely crucial. And we go through that in a few moments. Okay. Wood, we discussed that, covered that. CMU, we covered that. Thaw, freeze and thaw damage, that we don't have that issue very often here in California, but we have in other states. You're familiar with these veneers, the freeze and thaw phenomena behind the veneers that they fall from high rises and so forth. Six, documenting the failure. Generally speaking, when an investigation is involved, a forensic investigation of a failure, there's a process of preserving the evidence. Sometimes the evidence is destroyed. Whatever reason, they get destroyed, or they get lost. But in general, if they're available, they have to be preserved by law. Identifying the valuable physical evidence, preserving them for possible testing and evaluation for trial presentation, document the evidence, condition, and circumstances that would possibly change, because sometimes condition change and you have to do the assessment and documentation as soon as possible. Properly collect the failed components, unimpacted component, and piece mark them, piece mark classification. What is piece mark classification? I will explain to you in a few moments. That's also a term of art in law. This is an example of a subpoena order that, for example, when certain documents or evidence is required by other parties, they send this legal document, which is called a subpoena document. And there's a number on the bottom right-hand side. This is called bait number. These bait numbers are unique. Sometimes there are millions of pages of document in a case, and the only way to keep track of them is the bait number that is a unique number. So when you say, okay, I'm referring to bait number 627570, there's only one page that has that number, and that eliminates any kind of confusion. Okay, this piece is one of the pieces of evidence that I was talking to you earlier about that fatigue issue. This HSS member, this is the HSS, hollow structural section, failed at LAX under a jet bridge and caused serious injuries and for a pilot and a passenger. Okay, in a jet bridge. Let me go through and explain to you what. Okay, I took this picture. I went to LAX for the inspection after the fact. You know, obviously, a long time after the incident, but I still had to go look at this jet bridge on the right-hand side and the aircraft on the left-hand side. We have removed all the logos and everything, so we don't have to deal with any of that. But this is one of the top airlines. And the right-hand side, you have this structure is called jet bridge. Jet bridge, before like 40 years ago, 50 years ago, there was no jet bridge. You came down from the airplane by a staircase and you walk into the terminal. Even the small airports now still like that. They don't have jet bridge, but large airports all do that. And this jet bridge is, I don't spend a lot of time, but under this area, when you walk out of the aircraft door, you step here. Before you get here, you step on this cantilever member. And there's a cantilever member here, HSS, that failed. And that member, there's no redundancy. There was just one single member that was holding up. And the only reason that it failed because it was because of the cyclic loading. Why? Because over the course of 20 years, every day, 200, 300, 400 passengers step on this cantilever beam, the jet bridge, and they step out. So they put a load on the HSS section, then they unloaded it. Loading, unloading. Loading, unloading is called cyclic loading. Even it can be a reverse loading. It can be a loading that goes to zero, or it can be load that increases and decreases. That's identified as a loading that causes fatigue. Okay. Documentation. Photo documentation, it can be done by drone. It can be done by thermal infrared. It can be done by handheld videography, measurement and quantification, various kind of instrumentation, interview with eyewitnesses, and communication with other forensic professionals in the investigation. Now, based on ANSI and ASTM D48499, or the most recent ones, the standard guide for sample chain of custody is established. So it's an American National Standards Institute. It's not something that it is something that everybody will use and uses, and all uniform. Based on this section, you have in your handouts that the chain of the custody, it has to comply with this section and follow this. This is actually at the airport at the LAX that jet bridge failure, the HSS. You see the HSS is hanging from the bottom flange, and you see this jet bridge was at LAX, which is very close to the ocean and it's always exposed to chlorine from the ocean. Okay, and you can let me see if I have more pictures of this. I don't have more pictures of this, but here you see the corrosion. So what happened with cyclic loading? You get micro cracks, and as soon as you get micro cracks, of course, it's over the course of years. It's not one night, and then the moisture can get in, chlorine can get in, can cause the corrosion, and it makes the crack wider and wider and wider, and more cyclic loading, more corrosion, and eventually after 10, 15 years, this can happen in a brittle manner. conducting the investigation, identifying the debris, destructive testing. Some people get confused by, they don't understand the destructive testing. Most people, I've seen a lot of even a structural engineer, they don't understand what is the definition of destructive testing. Destructive testing means you take a piece of material, you take it to the laboratory, you test it to destruction. Steel, concrete, whatever. Once you test it to destruction, there's nothing left. It's all debris. And you can't take it back to the building and reuse it. And I've seen a lot of people, especially attorneys and contractors, they're very confused with the definition of destructive testing. When you go to a building and expose walls and you remove the wall finishes or ceiling finishes or to see what's the structural behind it, this is called removal of finishes. They always get confused. They say, oh, this is destructive testing. And I explain to them, this is, and they even put it in their legal document. Then they say, oh, the opposing party did destructive testing without our consent or whatever. So you're familiar with as-built drawing, original calculation, shop drawings, inspection records, and correspondence, such as RFI, request for information. Okay. This is this is that Mystery of Pumapunku series S1 E7 full episode. It's on YouTube. You type it in. It's in YouTube. I don't want to. It was 4.5 million several years ago. Right now it's 9 million, and also it was on Amazon to as a paid view. People went there, several million there. Now it's on YouTube without a pay. But anyways, you can go there, and History Channel had a 1-hour program investigating the causes of destruction for this structure, this site, ancient site, 10,000, 12,000 years ago in Bolivia. And they wanted to know why this got destroyed, why it got, so the 1-hour program, they went several different locations, Europe, South America, in US. They interviewed scientists and engineers and experts that are familiar with this field, and they wanted to find out what happened, what was the cause. And they gave me this assignment and say, Casey, if you are interested, let us know and do your research, find out what was the cause for this destruction. And I did that. So after they went talk to all these experts and scientists, at the end they came to me. So 10 minutes of that 1-hour program, of course it has some, the actual program was like 49 minutes. 10 minutes, the last 10 minutes was with myself. And they asked me, is it because of earthquake? I said, no. It's because of explosion? I said, no. I mean, I explained the reasons why no, not just yes or no. And they said, okay, was it because of the fire? I said, no. And I said, they said, what's the reason? I said, it's flood. It's a flooding. And there's only the flood based on my investigation. And I never went to this site. I told them, based on my investigation, the only reason that you can have this kind of destruction is flooding. And the interviewer told me that, hey, this is on the top of the mountains. What are you talking about, the flooding? How can water get there? I said, this is the only way this could get flooding. And I provided the reasoning. If you watch that video, you can see that. To cut the story short, after my interview, they went back to Bolivia and they found fossil of fish and sea animals in these areas, all on these falls and everything. So they confirm my theory. Anyways, so I will just play a few seconds and then I
Get a
stop.
better picture of just what this incredible site might have looked like when it was first built. We returned home to meet with Casey Himmatyar, a forensic structural engineer based in Los Angeles. With more than 30 years of experience investigating all types of structures and building materials, I knew that Casey would be the perfect person to analyze what Pumapunku was built to be, and what violent forces might have led to its destruction. Mr. Hamachiar? Yeah. Hello, Giorgio. Great pleasure to meet you. So, in your opinion, how do you think something like
Okay, I'll let you watch that yourself. It's 10 minutes and I don't think we have sufficient time. Okay. Now, a field protocol and tests. These are some of the tests that are performed, and I have performed them on my own cases and my investigations. This item, for example, as an example, is a seismograph, and you install this. These are a bit, there are different variations of these. These are not cheap. They're about $10,000 or $15,000 each. You install them on the site, and 24/7 it monitors the vibrations. And a lot of cases, vibration cause destruction, and I had cases like that. They can cause, when I say destruction, it doesn't mean the building collapse necessarily, but they can cause distress, separations and cracks on the structures. And normally, usually not on modern steel structures or modern structures they're not that susceptible on vibration. Mostly the older buildings, like buildings that are more than 50 years old, they can be susceptible, especially when they're built with masonry and concrete. So, field inspection in investigation methods, field instrumentation equipment, destructive testing, non-destructive testing. Non-destructive testing is, this is one of the examples, the seismograph or manometer or Schmidt hammer or GPR, ground penetration radar. And then the last item is about removal wall and ceiling finishes and exposure of all the structural elements. That's the section that I was talking. A lot of people, even structural engineers I've seen, get confused. They don't understand the difference between item number 5 and item number 3, but they're very, very, very different. Development of the preliminary result and findings, review of as-built document drawings reports, retrieve and review investigation data, review of the test result, compile and analyze collective data. Okay, this is slide number 40. Dr. Ashur, may I pause for like 1 minute and come back? Is that okay with you, sir? Dr. Ashur, are you there? Yes, okay. Thank you so much. I'm gonna allow for permission to pause for about a minute or so, and I'll be right back, gentlemen and ladies and gentlemen. Thank you. How are you? Okay, I'm back, ladies and gentlemen. Dr. Ashur, do you have me? Okay, okay, thank you, Dr. Ashur. Okay, so um, development of preliminary result and findings. Okay, review of as-built drawings, reports. Usually I review a lot of documents depending on the size of the case. Some cases I have like tens of thousands of documents and files. I obviously you can spend a lot on each file, but you have to review them. Some of them are more critical, and you have to spend more time and analyze them, summarize them, and everything. Some of them not as critical, like photographs, you just skim through like, I don't know, 10 seconds each. But you have to go through them. Some assignments, some investigation, they're very limited. You have 2, 3 documents at the most, which is very simple, straightforward compared to the other ones. Retrieve and review investigation data. So you go to the property, to the site, you use your non-destructive instrumentation, use visual observation, drone imagery, whatever that you need, or historical imagery by third parties that are available in addition to Google Earth or so forth, and review them. There are sometimes test results. When I say test result, not necessarily destructive test result, but you can have different kind of tests. You can have like some consultants come to the property, they do their own testing, soil test, they do their own moisture test, and so forth. And you eventually compile and analyze all the data that you collect. Okay, this is another example, very simple, straightforward example, very straightforward. There are 5 homes on the left-hand side, and there's a shopping plaza on the right-hand side. The red line represents a retaining wall, tall retaining wall, and the asterisks that you see are the locations of examination that we did, like photographs and so forth. And then you see this dotted line, that the dotted oval that I have here, red. There are certain trees on this particular side, but essentially to the left of this red light, they're all elevated lots, like about 14 feet taller than the parking lot on the right-hand side. So these are the backyards. Between the red light and the structure, the home, is a backyard, and none of these backyard have trees except this last lot. So this was one of the cases, the dispute between these homeowners and the shopping plaza owner. So as you can see, now this is a street view looking at that CMU wall. The CMU wall had deflected 7 inches towards shopping plaza. Okay, and that was the dispute, because once you have horizontal soil displacement, then you can have tilting in your structure. That's because this causes soil creep. The displacement, horizontal displacement, causes soil creep, which in turn causes vertical displacement under the structure. So this is a graphic for the image of what's going on. 7.7 inches of displacement, lateral displacement. The wall from the top of the slope was 7'9", but from the shopping plaza parking was 15 feet. And our theory was either the wall deflected or the entire footing deflected. Either one, we had to investigate. So this is the photograph of one location on the wall. You can see this is a true crack. You can see light on the other side, and you see the large crack in here. And obviously this wall is out of commission. Under a seismic load condition, this wall is not going to resist everything. And I don't know what's going on. You can't see any rebar, horizontal rebar here. Anyways. So that was one. Okay, and what's the summary of this case? The summary of this case, that they were telling us, the shopping plaza was telling these owners that, hey, The reason you have cracking and then this 7.5 inches, 7.7 inches displacement is because you have trees on your backyard. But then we went and we found out that there are only trees on the first lot, and all other lots, we took photographs and we saw evidence of the cracking, large cracking, similar to what I just showed you a few minutes ago. So there's no trees on these other 4 properties, but yet we still have cracking. So if we established that, okay, there's nothing, their claim that the homeowners' trees are causing these problem, that's baseless and it's not correct. Okay, now let's go to the next. This bulging in the stucco. You see here, I kept a horizontal, a ruler vertical, and from the top to the bottom, there was like 6 inches of difference. So this was bulged. This was bulging. This stucco, this apartment building was bulging. And what happened in this? The causation theory, I will explain to you in a few moments. Generally speaking, bulging can happen in the stucco for various reasons. If you have moisture built up, if you don't have the construction is not done properly, especially on the bottom of this, which is called, I believe, called Weebquit at the bottom. If it's not done properly, moisture builds up here and causes bulging. And if you poke a hole here, you see a void behind here. And not in this particular case, we found out that the reason was multiple layer of stucco. Because they applied multiple layer of stucco, that can cause bulging also, because the old layer and the new layer, when they apply, generally speaking, based on my experience, it can cause bulging. So that was one of the cases I wanted to share with you. Identify all possible failure scenarios, eliminate unlikely failure scenarios. Objective to converge on limited factors that are most likely cause of the failure. Key technical causes of failure must be supported by facts. Understand the process of design, construction, inspection, and maintenance prior to failure. So whenever we do an investigation on a building, we know that, okay, my work product, my report is going to be reviewed by several other experts. It's possible that it's reviewed by several other experts, sometimes very good, very, very good and knowledgeable experts. And if in our report we say something that is nonsense and is not objective and is biased, it's not going to help us. It's not going to help us. It's better to make sure that everything is objective and it's bulletproof. Nobody can find a flaw in it because sometimes some cases there are several parties involved, several experts, some of them very top-notch expert. They can review, and if there is something that doesn't make any sense, then it's not going to be look good for your client or for the author of the investigation or report. So having said that, I provide presentation on Dr. Ashur's platform and other platforms as well on a national basis, and they get recorded and they're available. People can watch them. And I tell you, I was in a deposition a few months ago, and there was like multiple cases, and this was the case already settled, so I can speak a little bit about it. There was a light fixture, heavy light fixture, 300 pounds, fell from after a few months that it was installed. It fell from the ceiling and it fell on the head of two hosts and the hostess on the restaurant and caused severe damage, injuries to them. And I was the expert on this case. One of the experts, there are many experts on this case. And so on the deposition day, there were several attorneys and they're deposing me one after another. And the last one, he said, "Hey, Mr. Himmatyar, I watch your videos. Didn't you say this and this and this on that video, that date, on that platform, Dr. Ashur or other ones and so forth?" And I said, "Yes." And he said, "I enjoyed your videos, but I think you said something contradicting." I said, "What was it contradicting?" And I explained and clarified everything, and there's nothing contradicting. So even these videos, the webinars that I do, they can be the opposing attorneys before, whenever there's a trial or whenever there's a arbitration or mediation or the deposition, they watch my videos and try to find something that they can use it to their best, to their own interest. Anyways, so we have to be careful. Everything has to be objective, and everything has to be based and backed by facts and scientific data. Back into this failure by the jet bridge, the failure region under. I took that picture myself. I took this picture myself, but this is not the actual. This is not the failed one because the failed one was gone. This is the new one. As you can see, they changed the size. This is much bigger now, and it failed from here. This section, and on the right hand side is aircraft door. On the left hand side is the jet bridge. So that's the area that it failed. Again, on the front, here on the bottom of the screen, you can see the body of the aircraft. And that's the actual piece that failed and is in the meteorological laboratory. They had to go through the test. And you can see here, this piece, the failed location, but they had to cut it because they had to do destructive testing. And so you see, this is the failed surface. You see the failed surface is here. This is the cut surface by the laboratory. They had to cut it so they can examine everything. And they took this piece here, you see this triangle piece, because they had, and this piece, because they have to do with destructive testing to find out the material strengths and other mechanical properties. So this is a closer picture. And this is a more close picture. I explained to you about the pattern of the corrosion and the cracking and everything. The pieces that are cut, again, they were tested to their destruction in order to determine their physical properties. This is a photograph by their specific microscopic cameras that shows. What is this? Do you see this? This is the HSS seam. All HSSs get welded here, and because they get bent, they're hot rolled, they get bent. So remember, cyclic loading and fatigue, the most vulnerable section is the weld section. Weld is the first part that gets damaged and very vulnerable. Okay, learning from failures. So we have about 20 slides left and we have about 15 minutes. I make sure that we have about 5 minutes time for you to ask any questions. So we go another 10 minutes and then we stop. Hopefully we can finish all this slide. Learning from failures. Understanding the failure mechanism or the mechanism to avoid future issues, improve building code and standards. Every 3 years they change. Ensure other structure are safe, and increase public safety. Remember, building code. We only have one building code in the entire United States. The model building code is International Building Code, IBC. Then each state has had their own building codes based on that model code. They cannot have a different model code. They can amend, add, or do some modifications, but they cannot delete any important section, life safety section, unless they have a public hearing, and they can delete something if it's gone successfully through public hearing, which in that public hearing, engineers, inspectors, architects, everybody participates, and they don't allow any life safety issue to be deleted. So that's, and remember, we have about 1,000 standards referenced in building codes, from ALT, ASTM, ISC, ACI, NAS, all kind of standards. They're called the standards, but we only have one code, either International Building Code or California Building Code, or whatever the specific state is. The other ones are all just standards, even though they're large, like ASCE 7 or ASTM or AISC, but they're not code. They're just called reference standard. Some people get confused. They say, oh, ASTM code or AISC code. No, they're not code. Example of historical failures we have from the amphitheater collapse before Christ. We have Tacoma Bridge. Probably you know about the resonance issues and the frequency of the wind and frequency of that bridge. You probably heard about the sea platform, Hyatt Regency walkway that you're very familiar, Northridge earthquake, and Genoa, Italy bridge collapse. We go through these very quickly together. If you haven't heard of the phenomenon called or known as resonance, I strongly recommend you look it up. Resonance. It occurs in oceans with large ships. It occurs with buildings and structures during the earthquake, and also it occurs with suspended bridges like this with wind. And in all these three instances, bridges, structures, and ships, talking about large ships, the phenomena is that when the frequency of wind or earthquake or waves get close to the frequency of the ship or a structure or the bridge, it will cause resonance. And the resonance amplifies the impact of that event, that external factors such as earthquake, wind, or ocean wave significantly. The magnitude becomes significantly increased, and it can become very destructive. That's why, and it also happens in wind turbines. Wind turbines sometimes experience that. I've seen that, and it causes problem with their foundations when this phenomena, when the periods are close. So we need to pay attention to that. That resonance here occurred and caused the collapse of this 1940 bridge that only lasted 4 months. The bridge, if you Google it on YouTube, you can see it just was so flexible, and the wind frequency, the resonance caused the collapse of this. Now, yeah. And there's a little more theories here on these. Negative damping, random turbulence, periodic vortex shedding, and it came down. Tacoma Suspended Bridge, the motion lasted 3 hours. Wind was 42 miles per hour. Frequency of the bridge torsional oscillation was observed at about 12 cycles per minute, which is 0.2 hertz. A support cable at the snapped, resulting unbalanced loading condition. Among other issues, wind drove the bridge to oscillate at its frequency, natural frequency. The natural frequency and frequency of wind and bridge were in resonance, causing the amplification of oscillation, excessive flexibility, and lack of sufficient stiffness. In earthquake, again, if you type in YouTube, resonance and earthquake, you can see example of this, that when the frequency of a structure, whether it's a flag pole, is a light pole, is a high rise, whatever, when it gets close to each other, then magnified movement can occur. Recent earthquake in Thailand is probably provide us with some of those. And this is the as-built drawings for the Tacoma Bridge. I highlight these two sections. The bridge was constructed with these members, and the asphalt on the top, the bridge here. And so that's the detail of that how it did. The next one is Norwegian, a platform, a drilling rig platform, and it was completed in 1976. 4 years later, it failed, and 23 individuals perished. They lost their life. The problem was again because of fatigue at the welded joint. Remember, I mentioned joints are welded joints are very vulnerable to fatigue. This is that platform. The platform here is on the right-hand side, floated. It's floating. And the failure mechanism occurred here near one of these. This is just a hydrophone, a device that collects all the information. So fatigue crack growth occurred from the pre-existing cracks in the insert fillet weld between the hydrophone support and the brace D6. So somewhere here. And this is that image as it was going down. And one of the columns, one of these columns, let me go up. Yeah, one of these columns, they salvage it and it's still in the museum, Norwegian Petroleum Museum. And this is the process from left to right that once this failure occurred here, this detached. Once it detached, it lost its balance and it capsized. This is a video of that. I just show a few seconds and then we move on. You can find it on YouTube, or let me see if I can play it.
Det gikk fort å få senket den omstridte riggen, mens Stortinget enda diskuterer.
Okay, we go next. This is a Morandi Bridge in Italy that took 40 lives in the city of Genoa in Italy, 2018, about 7 years ago. The bridge was fairly large. The scale, as you can see, this is 500 feet, this distance. And so the bridge was fairly large. You can see the human scale here on the very bottom in this little circle compared to the bridge. Overall, it was about almost 0.7 miles. But this specific span was about 200 meters, which is about 650 feet. And the support cables were here, cable encased in concrete. So the steel members were encased in concrete. Why they did that? Because they wanted to protect against environment and the corrosion, and because it's right underwater. But apparently it wasn't done properly. So why, when it was done properly, it was not done properly. So what happened is everything, they found out later when they took the pieces out, they found that everything encased inside that concrete corroded, and that's the reason for the failure. So the bridge lasted how many years? Let me see. I'm not sure how many years it lasted, but it wasn't long. It wasn't very long. But the moisture get trapped into these encased cables and cause the problem. Okay. Next slide. We have 2 more slides. I think we're on time because it's 7 minutes to 1. Assumption. Our assumptions must be consistent with the structure's behavior. We know software never substitute for solid engineering review. Back in the day when I graduated, steel, when I was at the school, the steel, those rulers, I forgot the names. if you remember, put in the chat. Engineering rulers used to be. There was no calculator or so forth. I entered university when I was in a 5.5 year program. It was 1976, I believe. And slide rule, a slide rule. Thank you, Mr. Runser and Mr. Lavin. Really appreciate. Thank you, gentlemen. Yeah, slide rule. It was a slide rule, but by the time I entered university in 1976, there were calculators you could use, basic calculators. But I still have a calculator. I don't know if you guys, but older guys like me, more senior guys like me, we loved Hewlett Packard calculator, the old one. They had RPN system, reverse Polish notation. It's a different system, but those calculators are not produced anymore by Hewlett Packard. You can buy them on eBay. The old ones, very expensive, $700-800. But a Swiss company bought they got the permission from Hewlett Packard, and they bought and they manufacture them now. So in fact, I bought one about $500, and it was shipped from Swiss, and I love it. So what I'm saying is that I always do my hand calculations. When I do a hand calculation first, then I do a software analysis, then I do back check again with calculators, my hand calc. I never ever trust software. And when any engineer uses the software, there's a legal terms. When you accept to use the software, it says you are responsible, not the software company. If there's a problem with your result, you are the structural engineer record, not the software company. So we have to be very careful, especially our young engineers. My own older son is he graduated from UCSD, structural engineering. He works with me, and young people, all these flooding of technology and everything, they just love to use software. But life safety is no game. We need to be careful. Hand calculation check. Okay, so. Okay, we did this. Okay, this is on the right-hand side, our older son. On the left-hand side, one of our associates. And I hope you enjoyed the presentation. I apologize for being a little bit late in the very beginning. And the software wasn't working. Again, technology glitch. Anonymous attendee said, Sly Luther, thank you. I'm looking at the question and answer panel. Still have my old John Corman. He says, I still have my old HP with RPN for engineering, similar HP for financial calc. Thank you so much, gentlemen. Yeah, a lot of my friends they don't want to switch. They love Hewlett Packard, and it's the way it feels, the buttons, the old-fashioned ones, the buttons. You make sure that you never miss any button, and no error, no mistake, and it's great to have those, to do the hand calculation always. Okay, gentlemen, ladies and gentlemen, let me take a look. Okay, I have an RPA calculator in the drawer at home. I should put it on eBay for. No, don't sell it. This is from Thomas Levin. No, don't sell it. Send an email to me. I buy it from you. Or keep it. It becomes more valuable. All right. I think John Cornyn, thank you, sir. It was a great pleasure and my privilege to be of assistance. I hope when you walk away today after this presentation, I hope I have provided you with some good information, and in your background, in the back of your mind, you can use those in your future investigations and so forth. And Dr. Ashur, I appreciate if you can send me the list of our attendees. Usually you send it before the presentation, but it's okay. So I have some kind of idea I want to make sure that I provided the best information that I could for our audiences. If there's any question, I'm available. And Dr. Ashur, is there anything you would like me to add? Thank you, Mr. Runser, for your compliment. Hopefully you put some good review for me. That would be an encouragement for me, so I can serve my future attendees more. Okay, I'm going to be here another few seconds because it's almost 1 o'clock. But Dr. Ashur, thank you so much for organizing all these seminars. And if there is anything else, you let me know. Otherwise, you can stop the presentation.